Hello everyone, and welcome to this overview of ORAN energy saving. In this video, we'll walk you through the energy saving key concepts and features that make ORAN networks more energy efficient without compromising on their core principles. Let's dive in. Energy efficiency is an end-to-end requirement involving all domains of Open RAN, which is recommended to be addressed upfront in the design of Open RAN solutions, whether it is RF channels being radiated, radio units, cloud, vRAN functions deployed on top of cloud, or intelligent management, all contributes to the energy consumption. We will start with categorizing the energy saving efforts into two sections, so that we can better understand the various approaches and technologies involved in achieving energy efficiency in ORAN networks. First sections is infrastructure energy savings, and another is RAN energy savings. In the infrastructure savings, we will start with hardware components, such as ORU and servers. The focus is on selecting power-efficient hardware components, optimizing power usage, and incorporating sleep modes to minimize energy consumption. On servers, we deploy cloud layer, and energy savings are driven by cloud software platform, dynamic workload management, and AI/ML-based optimization play key roles in reducing energy usage at the cloud layer. In the RAN energy saving category, it covers energy saving features at the radio level, such as symbol shutdown, cell switch off, and RF transceiver switch off. These features allow specific components of the radio to be switched off during periods of low traffic, leading to significant energy savings. And one of the most important aspects is also the intelligence and automation. This section focuses on leveraging AI/ML algorithms and intelligent management by the SMO and RIC to optimize and automate energy-saving mechanisms across the entire RAN functions. This includes predictive power saving and energy-aware traffic steering. On high level, these are the areas where energy-saving optimizations can be achieved. Now we will deep dive more into infrastructure and RAN energy savings by taking few use case examples. Let's start with one of the infrastructure energy saving techniques. To understand the concept of infrastructure energy saving, we need to explore two critical characteristics of CPU processor performance: frequency and voltage. As the CPU frequency increases, the voltage also increases, and thus power consumption also increases. But it's important to note that this relationship is not linear. In most of the cases, CPU frequency is kept always fixed, irrespective of the workload. But we will see how changing the frequency dynamically can lead to energy savings without impacting the performance. If you see here, there are multiple sites connected to Open RAN network functions, and each site serves some traffic. When RAN functions running on the servers are serving high traffic, and thus the CPU performance required is high, and so CPU frequency is kept at high, and so it consumes highest processing powers. Conversely, during periods of low traffic or workload, the CPU frequency can be reduced, so that energy consumption can be less, leading to energy savings. Another simple trick is that, when there is no pending work for the processor to do or there is no traffic, during these idle moments, we can put the complete CPU into sleep mode, or idle state, to save more power. In conclusion, cloud energy saving through CPU frequency management is a valuable strategy for reducing energy consumption in RAN applications. By dynamically adjusting the frequency based on CPU utilization and workload demands, we strike a balance between performance and energy efficiency. This covers an example of infrastructure energy savings. Let's discuss RAN energy saving use case example. We will discuss carrier and cell on-off example here. Mobile networks often utilize multiple frequency layers, or simply carriers, to cover the same service area. At low load, means, when the expected traffic volume is lower than a fixed threshold, energy saving can be achieved by switching off one or more carriers, or entire cell, without impairing the user experience. User equipment devices, previously served by the carrier or cell, will be offloaded by the E2 node to a new target carrier, or cell prior to the switch off. However, the switch off and on decisions are not a trivial task. There are conflicting targets between system performance and energy savings. Other carriers and cells will have to serve the additional traffic, and traffic is changing over time. E2 nodes support a number of techniques affecting energy consumption, which might also be load dependent. While energy savings for the switched off carrier and/or cell is maximized, the overall energy consumption of the network might even increase, so a lot of testing efforts are done before making it to the real production environment. Now, cell switch off, allowing an entire cell or a frequency layer to be switched off, leading to most of the RF and digital front-end components of radio unit to be set to sleep mode with a few seconds granularity. And this leads to energy savings into the radio units. Now, these decisions happens within microsecond of time granularity, and for this, a strong foundation of AI and intelligent closed-loop systems are required, where SMO and RIC comes into the picture. If you see this call flow diagram, defined into the ORAN specifications, cell switch on or off process starts with data collection, non-RT RIC performs algorithm for the same, and control to the E2 nodes, and which takes care configurations to the radio units. This diagram is just to make you understand that, while it looks simple, but there is a lot of heavy lifting done by SMO, RIC and similar intelligent platforms to achieve these kind of use cases. With that, we cover one of the RAN energy saving use case example here, and there are a lot of such energy saving use cases. To achieve energy saving use cases, whether for infrastructure or RAN domains, it has to be system level approach, where you need intelligent controls, like SMO, non-RT RIC and near-RT RIC platforms. And there is a requirement for energy efficiency KPIs, where measuring and reporting energy consumption is a baseline requirement for the management across the network. Each network element will therefore require dedicated KPIs. For each energy-saving use cases, a specified algorithm has to be written. In the ORAN terminology, these algorithms are in the form of X apps or R apps. And there could be multiple such apps for a single use cases. So, many companies are putting efforts to build these apps. One major feedback loop is also taken care, which is performance degradation of the network, because nothing is for free. If you want to optimize the energy saving, it comes at the cost of performance. It is just that how much performance degradation is within acceptable limits, without impacting actual customer experience. With that, we complete this chapter of energy saving. Thanks for watching.